Na na hey hey whoop boo whoop boo. So what we're doing here is we're looking at the conservation of angular momentum. Earlier on in the year we looked at momentum, and if we recall, momentum P equals a mass multiplied by some velocity, and that momentum is a vector. We talked about the conservation of angular momentum. Whatever momentum you have in the beginning of a system of objects interacting is the momentum you have to have at the end of that interaction. What we're looking at here is a very similar idea, but we're doing it in a rotating or an angular case. Now, if we think about momentum then being a mass times a velocity, in our angular or our rotational cases, we know masses are what we call moments of inertia. How difficult is it to accelerate an object in a rotational way? How easy is it to get an object to start spinning faster or slower? And a velocity in a rotating way is an angular velocity, omega. These two multiplied together give us a angular momentum, which we can use either a lower or an uppercase L for this. I'm probably going to use an uppercase L most often. Normally we would typically use like a lowercase L for a single particle, and uppercase L is for kind of like a system. Most of the time though, people just stick with uppercase L and call it a day, but sometimes you'll see this. So because this conservation of angular momentum exists, what we can effectively say here is that the momentum you have initially in a system of objects has to equal the momentum you have at the end of the system of objects. Or another way we could write this is that the initial momentum of the first object plus the second object equals the final momentum. Really, like, this is just what we're going to be talking about. I guess if you wanted to expand it, though, we could expand it by saying the initial moment of inertia times the initial angular velocity equals the final moment of inertia times the final angular velocity. So this is kind of like the most common thing we'll be doing right here. So we need to care about this whenever we have something where maybe we have an object or a system that is initially rotating and then something changes. Maybe something is taken off or something's put on. Maybe the system is rotating and it changes its shape. A common scenario for this is whenever you have like a figure skater, they're spinning on the ice with their arms like this, and then they change it so their arms like this, and now they're spinning faster. They've changed their moment of inertia, they've changed their shape, their mass distribution, and because of that, they're spinning faster now. A common way to see this, and what we would normally do in the classroom, is we'd put you on like some sort of spinning object. So a chair like that swivels like this is a nice thing to use, or even if you have like something else that rotates. But if you sit on a chair like this and you kind of put your arms out, and it works really well if you put some bricks or heavy weights in your arms, and you just start spinning. When you pull your arms in, you'll actually spin faster. You'll start speeding up. And this is the conservation of angular momentum. You've changed your moment of inertia. Whenever you bring your arms in, your moment of inertia goes down. It's easier for you to spin. And if your moment of inertia finally went down, then that means this has to go up, your angular velocity, in order to make this equal to whatever you had initially. So these are inversely proportional to each other. If one goes down, the other must go up. This is what we're going to kind of see here with this idea of angular momentum. We see it a lot, just normal day-to-day life. If you do gymnastics, like this is a big thing there, or diving, this is a big thing there. But really, if your shape of the object is changing or the mass distribution is changing, you're going to get a different speed here based off of that. So let's take a look at this example real quick down here. We've got a playground merry-go-round, and these are kind of hard to find anymore. They used to be very common years ago. If you go to a playground, they would just be sitting there, and you can kind of like have one of your friends sit on it, and you could push it. And then a bunch of people got brilliant ideas that if you hook a dirt bike wheel up to the back corner of it, or like an edge of the circle, you could throttle up, and you could get this thing spinning really fast. A bunch of kids got injured, and because they're huge liabilities, everybody took them out, but they're super fun. But you take a little merry-go-round, and it's got a radius of 2 meters. So let's draw a picture over here. So here's a poorly drawn circle. It's got a radius of 2 meters, and it has a moment of inertia, I, of 510 kilogram meters squared. So the I of the merry-go-round is 510 kilogram meters squared. It's initially turning at 50, or not 50, 0.5 rads per second. So 0.5 radians per second. So the initial omega is 0.5 rad per second. And all of a sudden, we take a 34 kilogram child and it says they jump on, but maybe we just toss them onto the ride. So take a child and make them green. They've eaten something weird. And they get tossed on at 1.5 meters from the center. So we're tossing them on here at 1.5 meters. What we need to do is we need to initially calculate the new moment of inertia of the child plus the merry-go-round. We've changed not only the mass, but how that mass is distributed on the system when we toss the child on. And then because of this, this merry-go-round was initially rotating at 0.5 rads per second. How will it be rotating now that this mass distribution has changed with the child? So what's the final angular velocity of the system? So what we can do here is, if we recall, moments of inertia, because they're kind of analogous to masses, they can just be added together. So a final moment of inertia here for the system will be just the moment of inertia of the merry-go-round, the 510, plus whatever the moment of inertia is for the child. Now, the child, while it is some sort of, four-limbed creature, we can think of it as just being a point mass in this scenario. The child is landing at this point. And because of this, we can think of the child as a point mass as just being a moment of inertia of mr squared. So what we can say here is that our final moment of inertia is going to be the 510 plus, and then the mr squared of the child. The mass of the child is the 34 kilograms, and then the distance the child is from the center is 1.5 meters, and we need to remember to square that. So 34 times 1.5 squared plus 510 is our final moment of inertia. So let's just run that through a calculator real quick. 1.5 squared gives us 2.25 times 34 is 76.5 plus 510. We get 586.5, and maybe you rounded, maybe you didn't, whatever, meters squared. Okay, so this is our final moment of inertia. Now, to find the final angular velocity of the system of the child plus the merry-go-round, we need to set up this equation from above right here. We need to take the initial moment of inertia, or the initial moment of inertia here, multiplied by the initial angular velocity, and that will equal the final moment of inertia times the final angular velocity. And that final angular velocity here, this is what we are looking for. So let's go ahead and plop in some numbers there and get that. We know the initial moment of inertia is just the merry-go-round by itself, so that's our 510. We know the initial angular velocity over here was that 0.5 rads per second. That has to equal our final moment of inertia, the 586.5, times some final angular velocity, which is what we are looking for. So let's take a look at that here. This isn't too bad mathematically. We just need to divide by the 586.5, divide by the 586.5. The units of moment of inertia and moment of inertia will cancel out, so that's nice, leaving us with just the units of an angular velocity, which is what we have. So let's just math this out real quick. Let's see, 510 times 0.5, or divided by 2, and then divided by 586.5 gives us a number. Now, before we look at this number, should this be spinning faster or slower? Our moment of inertia has gone up. So if our moment of inertia has gone up here, and it needs to equal some number from the left-hand side, then that means our angular velocity should have gone down. And when we look at this number, we get 0.43 radians per second which is less than 0.5. So we have slowed down our rotation a little bit. So that's a nice answer right there. It seems to make sense with what we have in the problem. One further thing with this angular momentum, which we've just conserved here, note angular momentum, as we wrote it, is a vector. To find the direction of the angular momentum, we employ the right-hand rule. You find the direction using the right-hand rule, and you do it in a very similar way to torque. What you do is you take your fingers, your four fingers, and you rotate them in the direction the object is rotating. So when I look at this picture right here, this is rotating around like this. So I would rotate my fingers like that, and when I do this, I see that my thumb is pointing out of the screen. And if you had this on a sheet of paper in front of you when you rotate that, that rotation would be counterclockwise, and your thumb would be pointing out of the table or out of the page. So you get the direction of the angular momentum using the right-hand rule, just like we did with torque. So it's another right-hand rule thing there. Pops up all the time in physics. Just a little FYI. And that's it. That's a quick little conservation of angular momentum. Hopefully it made a lot of sense for you. It's a lot of what we did previously in the year. Remember, moments of inertia adds just as masses, and then we're just conserving that angular momentum. Initials have to equal final. And with that, we're finished here. So not too bad, not too crazy. Y'all have a good one, and take it easy.